Hello everyone, welcome back to 3 Deviations. In today's video of single variable calculus, we are going to be introducing an optimization problem with a pretty simple example here. So in the last video, we talked about how we could tackle an optimization problem through differentiation. Of course, this is kind of a capstone of our Unit 3 experience because this is one of the real-world applications where we see differentiation come up. Now, of course, this is something that's going to stick with us throughout our journey through calculus. So while we might not be covering it much after we've finished with Unit 3, it's going to come back in a multivariable calculus playlist where this becomes a little bit more involved. But anyways, today, this problem isn't going to be particularly calculus heavy. It's going to involve finding the maximum of a parabola. And we're going to be doing a physics example for this. So I recommend you review differentiation if you have not done so already. Otherwise, let's get started. So we are going to just cover what we talked about in the video where we covered a physics example, because there's a really nice relationship between the position, velocity, and acceleration functions. Of course, if I have a function, the position function, x of t, that means that that's my position, right? And then if I want to take the derivative of x of t, I'm going to get the velocity function, v of t. And then if I take the second derivative of x of t, that's going to be the first derivative of velocity, which is also going to be the acceleration function, right? So we have this nice kind of relationship between all of these functions in physics, which is going to help us quite a bit to find some information in regards to our example. All right, so let's cover this example. So in this example, let's say that a ball is thrown vertically into the air. The height of that ball in meters after t seconds is given by the function h of t equals 64t minus 16t squared plus 8. All right. So the first thing I'm actually going to do is just rewrite this to make it look a little bit better. And we are going to get negative 16t squared plus 64t plus 8. This is going to be helpful a little bit later on, not in the first two parts of the problem. Now the first two parts of the problem are going to involve a little calculus. We're going to need to find the maximum of a parabola, and we are going to need to find the value of that maximum and the time of that maximum. So if I have my parabola here, it's actually not too bad. And we are going to have our maximum there. Let's pretend that line is tangent. And we are going to have a value here of t and a value of h in meters. So to find the time of maximum height, we're going to take the derivative of our height function. So h prime of t is going to be equal to, if I differentiate this, I'm going to get 64 minus 32t. So that means that if I set h equal to 0, or h equal to 0, so that means 0 equals, we got 0 equals 64 minus 32t. That means that t equals 2 seconds. So we've solved this. So we set our derivative equal to 0. We got t equals 2 seconds. We know when this tangent line is equal to 0 and it's at the maximum of our parabola, that means that we're going to have 2 seconds. So t equals 2 seconds. So we can put in one coordinate, 2. And we'll get the other coordinate right now when we evaluate this. So we are going to get, when we have 2, we're going to solve for h of 2. So h of 2 equals 64 times 2 minus 16 times 2 squared times 2 squared plus 8, and that is going to be equal to 72 meters. So 72 meters, and we can put that other coordinate up here, 72. Okay, so now we need to determine when it hits the ground. So this is going to involve finding the zero of a parabola. So I made this function look fairly nice to put into the quadratic formula, but we're going to make it even nicer by making a small adjustment. So we're going to get negative 2t squared plus 8t plus 1 That way our numbers don't grow too big when we're inside the quadratic formula. We're going to get t equals negative 8 plus or minus the square root of 64 plus 8 over negative 4. And that is going to yield a result of t equals 2 plus the square root, 2 plus 3/2 square root of 2 seconds. All right, so determined when we hit the ground. And something else that should be noted is if I keep the negative case, we're going to get a negative time, and that is not involved in this question. So we get 2 plus the 3 over 2 times the square root of 2 seconds. All right, so that is our problem on an introductory optimization problem. Next time we will be back to cover some more involved optimization problems involving some more complex functions that would require calculus. Of course, this problem could have been solved by completing the square and finding that maximum of the parabola. But of course, we wanted to incorporate a little bit of calculus into this calculus course. All right, thank you for watching. We'll see you guys in the next one. Bye-bye.